So I'm going to go ahead and start. We're going to keep going with the free response questions. This time from 2009, we're on question 6, and we'll have 4 and 5 for homework. So we're looking at parametric functions. That's functions defined in terms of time, and we'll be looking at relationships between displacement, velocity, and acceleration again. Okay, so here I've got, it's a little bit bigger, there we go. So I've got the velocity of this particle that's moving along the x-axis given by the table above, such that I've got our velocity in meters per second and our different times here. When the particle is at 0 seconds, our position is 7 meters. Okay. So first we want to estimate the acceleration at 36 seconds. How would I estimate acceleration?
Doing a Riemann sum.
Riemann sums are an estimate for an integral. If I integrate velocity, then I'll end up with displacement. So how do I go from velocity to acceleration?
I have to derive.
Derive. Okay, how can I estimate my derivative at 36?
We use the slope equation and plug in 40 minus 32 over 7 plus 4.
Okay, so our acceleration at 36 is our velocity at 36 is roughly y2 minus y1 over x2 minus x1. So that's v40 minus v32 over 40 minus 32 are the 2 points around that I have. Okay, and our velocity at 40 was 7. Velocity at 32 was negative 4. So that leaves us with 11 over 8.
8.
Okay, any questions on the first part? What are my units here?
Well, meters per second squared.
Perfect. Okay. For part B, first I want to explain what the integral from 20 to 40 of our velocity would mean. So what would it mean?
The distance traveled per meters from 20 to 40.
Okay. So this is our we're really close. This isn't distance, this is what?
Displacement.
Displacement, there we go. So this is the displacement of the particle from t equals 20 to t equals 40. Okay, the difference there is distance traveled would mean if we were here at 20 and here at 40, but we traveled there like this, and our total distance traveled would be really big, right? But our displacement would just be the difference in that position.
Okay.
Okay, and then I want to use a trapezoidal Riemann sum with 3 subintervals from the table to estimate the integral from 20 to 40.
Okay.
Okay, so we're gonna set up our trapezoidal Riemann sum. What's our first trapezoid?
From 0 to 20, so 20 times.
This is from 20 to 40.
Okay, but isn't that 3 sub-intervals indicated?
There is 3 subintervals, but we're estimating the integral only from 20 to 40. So I'm only looking at this part of the data.
Oh. So from 20 to 32?
Okay, if I did 20 to 32, there'd only be 2 subintervals.
Oh, okay. Now I see. Okay, yeah. So 5,
Okay, 5 times.
the base.
Okay, so we've got, for a trapezoid, we can have 2 different heights. We'll need to average those together. So you've given me the base already as 5. Now we'll get the average of our heights.
So minus 10 minus 8 divided by 2.
Perfect. Okay, then we'll go to the next one.
7 times minus 8 minus 4 divided by 2. And the last one is 8 times minus 4 plus 7 divided by 2.
Perfect. Okay, then we'll throw all of this together. So I've got, this is 5 times negative 9 plus 7 times negative 6 plus 4 by 3. Gives me, this is negative 42 plus 12 is negative 30 plus negative 45 is negative 75. What are my units?
Meters.
Meters, perfect. Okay, part C. I want to know, based on the data from the table, does the particle change direction? And if so,
So
when does it
it
change
changed
direction?
when it's when the slope gets negative, or
Okay, so if the slope changes from positive to negative, that would change direction. Or if it changes from negative to positive, that would also change direction.
so we find critical points where x is equal to 0, y is equal to 0.
If the, in this case, yes, if the velocity is equal to 0, since that's already a derivative, that would be when the particle changes direction. So, in which interval would the velocity hit 0?
Between 8 and 20, and
Okay,
22 and 40.
so I could say V8 is positive and V20 is negative. And then V32 is negative and V40 is positive.
So we don't have to calculate the exact points?
We don't have any way of calculating the exact points. But we know because our function is
Oh, okay, I see. Yeah.
differentiable, we know it's continuous. So we know the point will be somewhere on that interval, at least once. Okay, so the particle changes direction at least once on both 8 is less than t is less than 20 and 32 is less than t is less than 40. Okay. Any questions on C?
No.
Okay, last one. If the acceleration is always positive, and we know that the particle's position was 7 when t equals 0, then why does the position at t equals 8 have to be greater than 30 meters?
Um, okay. Um,
Okay, if you're not sure where to start, maybe give me a general form for position. So how would I find the position at 8?
integrate from 0 to 8,
Okay, I can integrate from 0 to 8, but I would also have to add what?
7.
Okay, 7, since that was x at 0. Okay, so I'm going to substitute. This will be x at 0 is 7. And then the integral from 0 to 8 of x of t, if my acceleration is positive, then the lowest that could possibly be is our velocity at 0, which is 3, times 8, our change in time, right?
Yeah.
If our acceleration is positive, then velocity should be increasing, so we'll know that it will be more than 3 times 8. The integral from 0 to 8 of x of t will be greater than v at 0 times 8 if
But
8
why
is...
times 8?
Because that's our change in time. Our dt here is from 0 to 8.
Okay.
So you could say I'm doing a Riemann sum. So we have our function where our actual velocity is going from 3 to 5, right?
Yes.
So as long as my acceleration is positive, means my slope is positive, my velocity is increasing. I should have more area under the curve than this left-hand Riemann sum, right?
Yes.
So I know the actual area will be greater than 8 times 3. My left-hand Riemann sum approximation. Does that make sense?
Okay. Yeah.
Okay. Um, we figure if the acceleration is positive, my velocity needs to keep increasing on the interval. If my velocity was already 3, then it always has to be greater than 3. So the least that this can possibly be is something super close to 24. That would be like increasing really, really, really small, 3.000 something all the way through. Technically possible would be 3 times 8.
Okay.
We know we'll be
Yeah.
more than that because we had to eventually get to 5, but so that means the smallest this could possibly be, our position will be greater than this. Would be 7 plus 24 is 31. Um, our position must be greater than 30 at t equals 8 if at is positive. As left-hand Riemann sum of 31 would underestimate um, the displacement. Okay. Any questions on what we did?
No.